Crankshaft and camshaft pickups are two of our more critical pickups and more critical things. As always, we want to talk about when to use this test. When do you pull out your big guns? Well, when you suspect an ignition problem that appears to be a timing related problem, or you have a crank or cam pickup code, it's obvious to do this test. This is far better than trying to use the flow chart, and you use this for a check for intermittent no start or die out. Now, crank and cam pickup signals, let's break them down, because if we break them down carefully, we find by covering a few types, we can cover both import and domestic vehicles. Now, ignition timing and injection timing all depend on crank and cam signals. The sequential injection and coil on plug is particularly dependent on coil and crank because it's selecting the right injector to fire, the right coil to fire. Now, no starts and intermittent operation, can't stress enough. Come here if you think you have a possible problem. Let's talk about the types we have. There are going to be several types that are currently in use. The magnetic pickups are fairly widely used. They have an internal magnet and a coil that responds to the proximity of ferrous, that means metals attracted by a magnet. Hall effect pickups respond to changes in magnetic strength. They usually don't have a magnet inside of them. However, Chrysler calls their Hall effects that have a magnet inside Hall effects, while GM calls theirs Magnetostrictive. A Magnetostrictive pickup is a Hall effect device that has a magnet inside and responds to the proximity of ferrous metals, just like the magnetic pickups does. And of course, there's a few optical pickups left around that respond to changes in light. Now, by knowing the types, we're going to find out our testing becomes very similar. Let's have a look at what it looks like on a schematic. Here's a schematic, happens to be a coil-on plug, and it has at the top a crankshaft pickup going across with shielded wires. And just beneath it, it has a camshaft. Both of these are necessary because the PCM is going to select when it's going to activate and fire coil number 1, 2, 3, 4, 5, 6, 7, and 8. All of these have to be selected by these two input signals. We're just trying to remind you how important they are. Looking at the schematic, I can see that my magnetic pickups are two-wire sensors. They don't have power. They generate their own voltage, and they have a ground reference called coil plus, coil minus. Let's look at what the signal looks like. Magnetic pickups usually generate an AC waveform that increases with engine speed, meaning trying to crank, this will be smaller. At higher speeds, it will be slightly higher. Let's look at how this is shaped. It starts at 0, goes up to positive, down to negative, back to 0. It's called alternating current. It goes positive and negative both. Now, this is the 50 millisecond sweep time. This is not off of a Ford. It's off of something different. Look what happens here when we move across here like that arrow did. Look carefully at the teeth. They're evenly spaced to a point, and at the top, they're not evenly spaced anymore. Down here, they're all the same size. Moving up to here, we have a larger space. This is how we generate this missing tooth, quote, unquote, wide space, larger than normal change in magnetic force because of this wide gap. Makes a bigger positive, makes a bigger negative. So this is characteristic of what you're going to see on magnetic pickups. It doesn't matter if it's BMWs, Volvos, Jaguars, Fords, GMs. They're all going to work very similar. They're going to have to match the target. And that's what we're going to talk about. Let's look at this one. Right here we look across, and we've got a series of small gaps between the big gaps. We've got 18 small gaps between the big gaps. Here's a different one, and look at this. We have 59 small gaps between the large gaps. What's the difference in these two signals? The target. Do they look the same? Do they test the same? Yes. High end we go right up to around 6. Low end we go down to about 6. We're looking at a pattern on the screen that shows us 1 revolution of the engine. And this is important. We want to see 1 revolution of the engine because we want to be able to make sure there are no missing or extra pulses. We're going to show you why this is so important in a little while. But take a look at this. You are looking at the same thing you saw before, just on a different scale. So even though they're totally different manufacturers, they test the same. Here's a General Motors early on with the cam shown. Now look across here. We have 1, 2, 3, 4, 5, 6, and then a space. We have 6 evenly spaced and too closely spaced. And this is the same type of thing. We're going from up in voltage, blue scale on the right, we're going from 0 up to about 8 volts, down to minus about 8 volts, a little over. It's a magnetic pickup signal. If we didn't know it was a 2-wire and look simply at this and says the blue trace on the right starts at 0, goes up to 8, down to 8. Your other thing you're seeing is we start introducing the cam. The cam is important to us. The cam stays low for a good part of the signal. Then it's high for part of the signal. Now, it identifies top dead center for us. Look, one double space, the cam is low. Just to the right, the other double space, too closely spaced teeth, cam is high. That's breaking the part of the difference between number 1 cylinder on top dead center for combustion and number 1 cylinder top dead center for exhaust. It shows us both cycles. We can do sequential injection. However, you will find that coil on plug, we need more than just 7 teeth in a revolution of the engine. We'll find something like this. Here's another variation on magnetic pickup. Now we said they all follow the same rules. This one has a varying amplitude. Varying amplitude is a function of the target. If the target is not perfectly round, the amplitude will vary like this. Okay, so we have a slightly odd-shaped target. That tells us something. We can count the teeth between the large gap. We also have our number 1 TDC shown here. Look, it goes low over here in this second white space. The middle space doesn't. Just like GM, this is separating top dead center from our others. So this is just as important. This cam or top dead signal separates number 1 on compression and number 1 on exhaust. The other thing you're going to find is the location of where this goes low. If you map them out, anytime we have a cam that is not timed properly, this will move either to the right if it's advanced or back to the left if it's retarded. Let me say that again. If cam timing is changed, somebody reassembled it, put it on the wrong tooth, it's not aligned properly, we've had a jumped timing, whatever the cause, we have computer control timing that's moved. It will move to the left to be retarded, to the right to be advanced. Keep that in mind. This is one surefire way of finding advanced and retarded timing that's been changed between cam and crankshaft. The only way these two line up properly is if the cam is lined up properly with its timing marks. Okay, we finished up our stuff with a number of different variations. We saw a lot of different magnetic timings. They all work the same, with the target determining the number of teeth and the shape of each signal in the rotation of the engine. We need to know how many are there. We need to find missing and extra ones. There must be no missing and extra pulses in the pattern. The signal must match the pattern of the target exactly. Now we're going to look at the relationship to ignition timing control and the pickup signals later after we cover the other types of pickups. We're going to talk about the differences between Hall effect, magnetostrictive, and our magnetics. Our first difference is Hall effects and magnetostrictive pickups require external power and ground. They are not self-powered the way the magnetic works. The signal is a digital signal, means it's going to stay above 0, goes from 0 to some higher voltage. This can be anywhere from 5 to B+. And the signal's shape and frequency is still determined by the ferrous metal target. Remember, ferrous metal is simply metal that's attracted by a magnet. Here is an example. Right here we have 8 volts coming out of this Chrysler. It's going to go over here to a splice and supply power to both of these sensors. 8 volts is supplied to the cam sensor at the top and the crank sensor at the bottom. Also required is going to be ground. We have signal ground coming over here, getting to a splice, splitting, and going to both the crank and the cam sensors. One thing we have to worry about here, we did not have to worry about with our magnetic. Do we have a good power, good ground? If we lose power or ground, we'll lose 2 sensors at once. We'll have no signal out of the crank, we'll have no signal out of the cam. This is an important finding. Watch for patterns. Let's move along and talk about the signals. We're going to have a separate signal coming in here for the cam. It's going to be a 0 to some voltage. In this case, it's 5 volts. And let's see what it's going to look like. Here is a magnetostrictive because it has a magnet inside. It's not being blocked from another magnetic target. Now, this pickup, when it crosses those 2 gaps, is going to produce two signals. So as we cross here, boom, we get two small, skinny signals. Do you see the similarity between what's mechanically on the right and what you see on your scope? Understand, the scope is going to show you exactly what you're looking at. Do you have the right number? Does it match it? Here's some examples of problems we've run into. This is a GM with a Hall effect. It's got dual Hall effects. It's got an 18X and a sync signal, and they both go over. First, the sync signal comes in on pin H of the DIS module, and the 18X signal comes in on pin G. This module does more than most modules on today's cars. It's going to have a separate cam input, separating us into 720 degrees of engine rotation. And then, when the process is done, it's going to have a 3X reference out. This is used for spark above 1800 RPM, but below that, the 18X is used. And we've got some other complications like electronic spark timing, EST up there, and bypass. That's beyond the scope of this. That's getting into ignition systems, and we'll leave that for our courses under guided diagnostics. Let's look at what we can see with a scope and how we can diagnose this complex system and how they all interrelate. First of all, we're going to go hook up our leads here, and we get something like this. First, at the bottom, we have our cam. The cam input, the two signals are 720 degrees apart. So they're high there, and then they're low back over here. So we have two low spots, 720 degrees apart. And we have the other two signals. The 18X signal is here in the middle. It's 2 revolutions. So the 18 teeth coming off of that gear is going to show up as 36 teeth between these signals. They're evenly spaced. Now remember the pattern we had back with magnetic pickup? We had a special gap that said something different is going on. There are no gaps here. They're evenly spaced. The module needs more information to determine where the engine rotation is. This is where our sync comes in. As we look at here, our sync, we have varying pulse width signals. They're evenly spaced, but they are varying widths. Look at the pulse width. This is narrow. It is the same width as one 18X pulse. The next one over is a medium width. It's 2 widths of an 18X pulse. And the next one is a wide pulse, and it's 3 pulses wide. Those 3 pulses together represent 1 engine revolution. There are 6 of them between the cams. That tells us something. When we saw 6 between the cams, there's 3 per revolution. It only takes 1/3 of a revolution for this module to determine which pair of spark plugs to fire on this DIS module. It doesn't care where it's on compression or exhaust. It fires them all at the same time. It fires them on top dead center. It's got a wasted spark. Remember, the computer is going to have to do the actual firing. So down below here, we've put in our 3X reference to the computer. Now some people get confused because the sync signal is 3X, meaning 3 per revolution. That is the same as the 3X signal sent to the computer. It is not. You're looking at the sync at the top, and at the bottom, you're looking at our 3X reference. Now, there's a relationship in time, but there's certainly no relationship to these. There is a relationship here. Let me show you the relationship. The relationship is to the 18X signal. Okay, let's look at this. Starting over here, we have the leading edge of the green trace at the bottom, which is our crank reference, is going up at the same time this pulse is going up. And we go across 1, 2, 3. On the 4th one going up, we have the same rising edge. So we have 3 complete pulses shown, and then at the leading edge of the 4th pulse it goes up. Let's look next door. 1, 2, 3. On the 4th pulse going up, we come off the low and go high again. And then 1, 2, 3, 4th pulse goes back low again. 1, 2, 3, 4 goes low again. If you look at this, what we want to tell you and what we want you to see is that the highs and lows here are totally using every single 18X signal. Let me say that again. Down at the bottom, our 3X reference, which is the computer is going to vary in time to fire sequential injection and to fire our plugs, our ignition system. It's going to use every single 18X signal to create that information. Now, whether it's created in a module like this or whether it's created in the computer. What I'm trying to stress is the principle is the same. All of these are going to be used to determine when to fire the spark plugs. We cannot have missing pulses. We cannot have extra pulses here. And the only way you're going to find these extra missing pulses is to have enough pulses on the screen to study like we're studying now. Do not try to look at one single pulse. That is the point we want to bring home to you. The lows take the same length of time as the highs. It's the same thing. All of the pulses are used to define these pulses at the bottom. And the pulses at the bottom, that's what we're going to use. For advance and retard of spark timing, we're going to decide by them to use injection. How do we know that? Well, we're going to look at some other signals here and talk about them. Here's a combination signal. We keep saying you've got to match the number of teeth. Well, in this particular case, we have 3. Blue scale. We're going up to 5 volts. Looking at the low parts, it goes down to 0. What is that crank? That crank is obviously a Hall effect. But as we look at the middle, the TDC, we look at it and it's varying in amplitude around 0. On the right, we see 0 volts. It's going up to 2 volts, going down to about 1.2 volts. Notice it goes up. This is 720 degrees of rotation again. We're identifying top dead center. When the red is going high and the blue is going low, we know we're on top dead center. Again, we're going to stress the alignment of where this happens tells you exactly what the alignment of the crank and cam are. If you suspect you have jumped timing chain, you expect you have a misaligned timing chain, look here and it will tell you. If you get a code that says timing is advanced or retarded, the red trace will move left if it's retarded. The red trace will move right if it's advanced. So let's go back and look at some more information. Another different vehicle. This time we're just showing you that sometimes we have the varying pulse widths just like we had with our magnetic pickup. This is a 0 to 14 volts Hall effect. It's got a couple different shapes. We know if we look at the target, it's going to have a bunch of evenly spaced and 2 that vary width. That again tells the computer where top dead center is. We're going to need a camshaft to tell us when number 1 is truly on top dead center. But you need enough pulses and enough time to get a full pulse train. You need to see the whole thing, and you need to be able to determine that. Here's a 12 volt, evenly spaced. We have to have something else to tell us what's going to be doing this. We measure it by simply looking over here on our left. So when we have signals like these, we don't let them throw this. We can use them, we can analyze them, and we can look at them for a relationship between crank and cam. It's a good idea to put both of them like this. You just saw 2 systems up there. Without the cam or the TDC, you have no idea who's on compression and who's on exhaust. And those can be important features. Now let's take a look at a combination of 3 signals. The red at the bottom, the right scale on our scales, is the cam. It's going high, low, high, low. We've got cam that's wide, space, narrow, and then more space. You're looking again at 720 degrees of engine rotation. To get the full cam in, you need to slow the scope trace down. You don't want it to be too fast. Many people try to focus in and look at one of these patterns. There is no one pattern to look at. We've got to look at the overall picture. Now we're going to do something special here. This is a Chrysler. It's a 4-cylinder engine. We have a wide pulse and 3 narrows. Next, we have 4 narrows. Then we get back over here and we got a wide and 3 narrows. Then we have 4 narrows, a wide, 3 narrows. We have a pattern, a very definite pattern in our crankshaft. And just above that, we have also put in the injector. This is injector number 1. Now, what do you see unusual about this as you look at it? Injector number 1 is always nestled right after the long pulse before the 3 narrow pulses start, when the cam signal is low. If the cam signal is high, we do not have an injector pulse. This is sequential injection. What you're seeing is how the cam is used in conjunction with the crankshaft to position the injector signal. Let me say that one more time. You're looking at how the crankshaft signal and the camshaft signal are used together to figure out when to inject fuel, and the next part, when to fire the fuel that's been injected. We'll show you that part so you don't feel left out. But here's our injector number 1. This is a sequential injector. We frequently use sequential injector number 1 as a good way to synchronize our scope to 720 degrees. When you see 2 pulses of the injector on the screen, you have 720 degrees. They're nice and evenly spaced, and they're easy to trigger on. Look at the bottom. We have ignition. It's happening after we have injected the fuel. Oh, that seems to be a good time to do it. So here we've injected fuel. Now we're going to have ignition. And the ignition shows up like we saw before. It says DIS. Every time we have a wide pulse, we're going to have ignition. Let me say it again. Every time we have the wide pulse with the 3 narrows, we're going to fire one of the coils. One cylinder will be on wasted spark, one cylinder will be on power stroke. That's not a problem. We can speed this up so you can see it better. Here they are better. We've been saying all along that these 2 critical signals are going to be used to time fuel injection and to time the spark. We've just proven it to you. Now, why do we bother looking at secondary ignition? I want you to look at the bottom. That dark spot there in the middle, that's the spark. And just as a cursory look at that, I can see lean fuel mixture. I can see misfires. Please take the time to go study secondary ignition, because there's a world of information right there for you. But what we're showing you here is that we can see exactly how they line up. They're lining up in their position based on the number of crankshaft signals they see. If there's extra or missing crankshafts, we're going to move them to a different spot in time. Cannot say how important that is. So Hall effect, magnetostrictive pickup signals can be temperature and voltage sensitive. Let me say it again. They can be temperature and voltage sensitive. We have seen these rare occasions where intermittent problems can only be found when everything is just right. We had one vehicle where if you just disconnected the alternator, this horrible sound in the engine and sudden change would go away. Not surprising it had a new alternator. We had a Hall effect that was weak, and when voltage was just right, around 14 volts, and temperature was just right, you occasionally lost one of the 18X signals on that pattern you just looked at. And when one of them is missing, we messed up all those nice little dotted lines we had. So keep in mind, intermittent problems may be difficult to identify in service bay. Set your scope to get a full view of at least 1 revolution for the crank, and cams are going to require 2 revolutions. And use our trick. Set triggering to number 1 injector because they're all evenly spaced. It's sometimes hard to trigger on unevenly spaced signals. So crank and cam pickups are different, with each manufacturer having their own designs. But follow the examples we used and you can check. Imports, domestics, it doesn't matter. The rules are the pattern in the signal must match the target. Doesn't matter if it's a magnetic pickup, Hall effect, magnetostrictive, the pattern in the signal must match the target. This is not rocket science. This is easy. Look at what it's looking at. See if you see the same exact pattern on your scope. And because ignition and ejection timing are determined by these 2 signals, you cannot, as we showed you, have any extra stuff. Use specific diagrams for vehicle-specific information for your diagnostics. It'll speed everything up. And remember that Hall effect and magnetorestrictive pickups require power and ground to operate. Do not ignore those. If you haven't got power and ground, it's not going to work. Our diagnostics do not say if the pattern is bad, change the pickup. We told you they must have power and ground to work. If the pattern is bad, see if the target is bad. Once in a while, like in some of the Chryslers with a flex plate on the back of the flywheel, it cracks and develops breaks in it, and it messes the pattern up. What's the rule? The pattern in the signal must match the target. If the target's goofed up, you'll get a bad pattern. Listen, use this. It works, and it's simple. Don't make it rocket science. It's very simple. Doesn't matter if you're checking imports or domestics. There's a few variations, but don't let them throw you.